Welcome, everyone. Today, we're going to explore a practical question that many developers that have tackled with AI over the years have dropped in their minds. How simple should our LLM integration be? The main aim of this presentation is to observe a spectrum of integration approaches, from single LLM calls to multi-step workflows. And ideally, by the end, we will have learned two things: how to identify where on the spectrum our application belongs, and when additional complexity is really justified. So the core principle is surprisingly the most straightforward one. We must find, in every case, the simplest solution that solves our problem. On the left, we have a simple pattern with just three core components: a core LLM, a retrieval system, and some tool functionalities. So in this streamlined approach, we offer some key advantages for our apps. It's maintainable, it's debuggable, it's adaptable, and most of all, it's purposeful. And on the right, we have a more complex scenario where the framework contains multiple interconnected components: an LLM, a large language model, a router, an API, or even multiple APIs, cache layers, vector DBs, embedding stores, a parser for the prompts, validators, and those are just few. And as you can notice, all of those add to our capabilities, but also introduce some drawbacks. The framework is harder to maintain, difficult to debug. Obviously, it's a bit more brittle to changes, and as a result, carries overhead cost. We are already on slide number 2, and I've already mentioned maintainability twice. The value of maintainability can't be overstated. When an AI system finds its way to production, and it will, something will break. Something inevitably is going to go wrong. And we want to build a system where it's easy to reason and fix. And the same goes for adaptability. The LLM capabilities, actually the LLM models and by extension the LLM architectures over the last few years have evolved, and rapidly, if I may say so. So if we keep it simple and we build it even simpler, then we can create systems and architectures that are faster to update and enhance. Always keep in mind for this presentation that simplicity is a deliberate design choice. It's not a limitation. What we're seeing here. So in this spectrum, when we are integrating LLMs into our applications, we are basically operating along a spectrum of complexity. At the simplest end, we have single LLM calls, direct interactions. You can imagine a Python one that calls the OpenAI API directly. And it's usually optimized with a well-crafted prompt and maybe some retrieval options. And as we move rightward, we encounter some new patterns like chaining, routing, and parallelization. Don't worry if you don't know this stuff. We're going to analyze them later. And these patterns aim to decompose tasks or direct them appropriately. And further along on the right, we have advanced workflows that enable more sophisticated capabilities and basically add to our system. When we go full to the right, we encounter full agentic architectures, which these are basically systems where LLMs maintain their own state and are also responsible on how to handle processes and how to direct them over time. This is very important. At every step along the spectrum, we have an increase in capability, from single LLM calls to simple workflows to advanced to full agents. But that also introduces some other things that we are not very fond of: additional complexity, higher costs, and potential failure points. So moving rightward should always be justified, and we must always have clear requirements that can be met with simpler approaches. And with that, we are reaching our first basic building block. You're all familiar with an LLM. In this picture, what we see is what we will start calling an augmented LLM. At its core, it's the language model itself, which provides reasoning and generation capabilities, all things we are familiar with. And around it, we have three different components. We have retrieval systems, systems that allow the model to access knowledge outside of its training data by connecting to a company's documentation, database, or even the internet. We have tools which enable the model to perform actions in the world, from simple calculations to API calls and even database operations. And lastly, we have memory component, which it basically helps with handling the context limitations and help us overcoming it. So, for example, if we are using an LLM that has 200,000 tokens as a context window, we can help expand it by playing around with its memory. And the structure you see here can be built and can be used as a standalone, can be used as a foundation for most of the use cases that we are working on a day-to-day basis, but can also serve as the foundation for more complex architectures. And having said all that and having first touch of our fundamental building block, I'd like to start focusing on what's important between these components, meaning the LLM, its retrieval system, its tool functionalities, and the memory limits. Between all those four, it's very important that we always maintain clean interfaces so that we can keep it simple in regards to integration and troubleshooting. Integration matters because when we have a clean interface and we have a simple integration, we can more or less easily explain what's actually happening with our LLM integration. And troubleshooting matters, it matters a lot actually for engineers because it helps us preserve our sanity when we have production incidents with these applications. Let's go over and see some examples. So, regarding prompts, when we're talking about prompts, it's very important to keep using a consistent format with clear delineation between instructions, examples, context, and questions. We must start thinking that prompt design is basically similar to the API design. So just like we create a contract for an API, we're now creating a contract for how information is exchanged between systems. So always treat your prompts as living code, test them, version control them, revision them, and iteratively improve them. Moving on to tool functions. Here we have tool definitions. The quality of our tools is greatly affected by the tool documentation that we have written for it. A well-documented tool, like we can see on the left, provides a detailed description that includes the specific purpose, parameter documentation explaining exactly what's needed, and a concrete usage example. As you can see here on the example on the left with the blue, we can see that this is a tool called Search Database that takes customer IDs, and the customer ID should be a string and required. If we go to the right, we will see that a poorly documented version basically offers minimal or even convoluted information, and that leaves the model to guess about proper usage of the actual tool. So, like we think when tool documentation comes to mind, we should basically tackle it again as API documentation. And like we have invested for the last few decades some time and effort in creating human computer interfaces, we should also need to apply the same care on what we will come to call agent computer interfaces. You have to keep in mind that LLMs basically understand our tools through the lens of the description that we provide them. So in that case, every detail matters. And the last one, and a favorite of mine, basically here we're comparing clean versus clutter interfaces. Clean interfaces also include error handling and robust fallback mechanisms. For example, bring your mind, how should the system respond when a retrieval finds nothing relevant? Or what happens when a tool call fails? Designing these pathways up front helps us prevent cascading failures later down the line. So this can be a little bit hard to visualize, so let's go over some examples. Let's say we have retrieval failures, and the model, instead of just saying, I couldn't find an answer, we can have a well-designed prompt, a model in place that can come back to us answering like this. I don't have specific information about that model number. Could you verify the number? Or even better, would you like me to help with similar products in our catalog? For tool errors, in most cases, we just simply give up, and at best, we just throw an error to our user. And here, even though it's a bit more difficult, we should start implementing retries with modified parameters. Again, a similar example, say we do a product search, and the exact terms that we use for the product search fail, right? And instead of throwing that failure back to the user, we can automatically broaden it with search or even check for common spellings. And if nothing of that works, then later we can report failure to the user and the user can continue with his search. And the last example on context limitations. We talked a few slides back about memory. In order to overcome memory limitations, we need to train our system to recognize when it needs more information. How does that translate into practice? We can codify the intent of, instead of making assumptions, we can have the model ask clarifying questions beforehand. So let's say we're working at an investment firm and we are communicating with our organization's chatbot, right? We want to come up with investment strategies for the next quarter. And we don't know how to do that. And the model, instead of throwing a random answer out there, can ask us beforehand, to help you with your question, could you specify whether you're interested in short-term or long-term investing? What I want you to keep from these examples is that, oh, sorry. Let's proceed with the next slide. So we talked previously about the fundamental building block that is the augmented LLM, which is basically a large language model with retrieval, tools, and some memory capabilities. This is on the left. On the right, you can see a simple Python implementation. Disclaimer, this is a very simplistic approach just for the purpose of this presentation. You can see here that the retrieval happens within the prompt or even the LLM call itself, and that everything is handled in a single function with minimal complexity. We basically retrieve the relevant documentation, format them in the query, and lastly generate a response. And all of this happens in just 10 lines of code. So we basically have the equivalent of a working RAG system. There are no complex abstractions to debug. There are minimal dependencies, even if we use libraries outside of the standard library of Python. And you can more or less see that it's easy to understand the entire flow at a glance. And this is just the simple version. Let's see what happens. Let's see what happens when we proceed with a diagram that you might be familiar with. What you're seeing right here is a multi-step RAG workflow. You can see that we have various steps in the process. We need to encode at different points in time the additional documents and the queries. We need to index them. We need to run similarity searches before loading them to the vector databases. We need to run the embeddings. And after some steps, we need to combine all of that with the original prompt and throw it back to the user. And how this translates, you'll notice that, again, this similarity is more than 10 lines of code, but I try to codify it a bit, so I can give you an example of a Python implementation, at least outside of the standard library. Here, we have the steps codified. We have the query encoding as embedding. I even add a re-ranker for relevance, which is an optional, it is an optional step. And the pain point here is that if you notice the statements, for example, query embedding, similar docs, re-rank docs, they are not simple statements. They are function calls to layers of abstractions. And if we had an editor and we could go see them, we could, peek behind the curtain and see that there is more complexity waiting for us. And when we have those two cases, the fundamental building block, which is the augmented LLM, and the more traditional approach like the multi-step RAG, you can start wondering, okay, cool, so how can I start deciding on when to add complexity and how to add it? Based on my limited professional experience on AI engineering, I usually try to approach such problems having around 6 pillars. So I try to consider these factors. When we want to consider a use case fit, I think it's easy to assume that a simple approach excels at general Q&A, basic classification, and straightforward summarization tasks. If that covers your needs, great. You don't have to add anything else. You are good to go. But a multi-step approach becomes valuable for knowledge-intensive tasks and complex document analysis. Basically, if your retrieval quality is critical and the top priority, you really can't escape a RAG approach. Going with development effort, which is also known as engineering hours, or in some other circles, story point estimates, this is something that we must put some significant thought beforehand, because going with a simple approach, it's usually very easy. It's something that can be implemented, as you saw, in a few lines of code. It will take from a few hours to a few days, and by a few days, I mean less than a week. And that makes it perfect for quick prototyping and validation. On the other hand, a multi-step workflow typically requires more than a week to a few weeks, and that leads us to maintainability. I think it's the third time that I mentioned maintainability. You see, maintainability is often overlooked until we are really in production and things start breaking. They always break. And in that case, simple approach has fewer moving parts, fewer components, meaning that it's easier to debug. A multi-step workflow approach, on the other hand, introduces more components, meaning we have more failure points to take into account. And all of that requires robust monitoring and testing. And monitoring and testing is something that adds to the development effort that I mentioned previously. That being said, if we want to handle with precision the performance control of our application, a multi-step workflow approach is better in that case, because we have different components, we have finer-grained control over those components. On the other hand, a simple approach is usually like a black box. As you saw, on the same call, we do the prompt design, we send the request, we do the processing, everything happens in one step. And I'm going to close those 6 factors with latency and cost, which are very practical considerations. And these two directly impact user experience and operating expenses. It's easy to observe that when we go with a simpler approach, we have fewer requests in the 1 or 2 seconds, and lower costs as well due to fewer API calls and model invocations. So, on the other hand, with a multi-step workflows, depending on the latency, we'll have higher latency and higher costs as a result. I reckon that we've gone over these 6 factors and you're still not clear on how to take a decision. The conclusion is that you can't safely decide on how to approach and tackle AI LLM integrations. And the key takeaway that I want you to have is that neither of those two is universally better. It's basically about striving for the right fit on our specific requirements each time. Now that we have gone over some simple blocks around LLM integration, I'd like to start exploring how we can compose all of those principles and create simple workflow patterns. These patterns basically represent the first step beyond the single LLM calls that we showed. We, from now on, keep in mind that we trade some combination of latency, cost, or complexity for potentially improved task performance. We're going to start with prompt chaining. Prompt chaining is perhaps the simplest workflow, but it's also remarkably powerful. It involves breaking a complex task into a sequence of simpler steps where each LLM processes the output of the previous one. As you can see in the diagram, we have the LLM call 1, create an output 1, which it passes to LLM call 2 if it passes the validation check. Now, this approach sounds simplistic. It's not. It has several advantages. First, it makes each individual step more manageable. So instead of asking an LLM to solve a complex problem all at once, you're basically asking it to focus on one aspect at a time. And moving on that, we can create natural checkpoints. It's the gate you see on the diagram, where we can validate those outputs and we can introduce fallback mechanisms. We can write some better handling and so on before proceeding on the next LLM call. a common example in this case, and it's something I think we're all familiar if we're using the web UI versions of LLMs, it's basically content generation. So imagine we need to generate an outline, right? An email, a marketing campaign, or even description for a Jira ticket. And so we start with generating an outline. We proceed with asking a second time, in this case, a second LLM, to expand it in the draft. And finally, we can have a third call, polish it, and produce the final text. And each step builds on the previous output, but has a simpler, more focused task to do. And the primary trade-off is basically latency, because in order for one LLM call to proceed, it must wait for the previous one to complete. But to be honest, for many applications, and actually for most of the applications, the improved quality and reliability that comes outside of that pattern is enough to justify this cost. And remember, when we're talking about latency, always take in regards the scale. A latency of 2 seconds is not the same as a latency of 20 minutes, and definitely different from a latency of 2 days. Here you see a simplified version in Python. Very, very quickly, we have a function called chain. It accepts an initial input that's a string, and it's basically a list of prompts. And it iteratively processes in the for loop each prompt, feeding the result of each step into the next. The second pattern is routing. Routing addresses a very common challenge that we're all familiar with. It's that of different inputs require different handling approaches. So rather than creating a one-size-fits-all solution, routing uses an LLM to classify the input and direct it to specialized handlers. As you can see in the picture, we have an LLM call router, and based on the decision, it directs the input on LLM call 1, but it also analyzes and identifies LLM call 2 and LLM call 3. A very simple example that comes to mind is that of a hospital triage system, where we have patients with different needs, and we need to allocate them to different specialists. So in similar fashion, an LLM can analyze an input and determine the most appropriate processing path. An example more catered to our cases is that of a customer service application. I think we're all familiar, if we haven't talked already, with customer service bots through banks or telecom services. In that case, the prompts vary. The input from the queries from the user varies, and they vary by a lot. We might have technical questions, and if we're using a routing pattern, in that case, technical questions might be routed to a prompt optimized for technical explanation, while inquiries about financial or billing information will go to a prompt designed for financial information. Now, we have different specialized paths. The paths are the LLM calls in the picture, and this can be optimized independently, leading to better overall performance. And that's actually the key advantage of the routing pattern. It's the separation of concerns that takes place. Instead of creating a single complex prompt that handles, again, all possible inputs, which inevitably at some time it will compromise somewhere, we can create multiple focused prompts that excel at specific cases. And the trade-off here is kind of considerable, since we create specialized paths based on a use case, meaning that we have to tackle the additional complexity of maintaining all of those specialized paths, usually through our code. And as you can see here, we have a root function. It takes an input and a dictionary, and the dictionary inside has the mapping of the root keys to the specialized prompts. So we use the LLM to analyze and classify the input, we extract it, and we then process the input with a selected specialized prompt. Let's proceed with the final one. So the final pattern is called parallelization. And I think the name gives the way, but it leverages multiple LLM calls simultaneously, meaning at the same time. So unlike the previous patterns, where both of them were inherently sequential, a step at a time in most cases, parallelization distributes work across multiple instances. Now, this is not apparent to the diagram, but there are two variations of this pattern. There's the sectioning and the voting. The sectioning basically breaks a large task into dependent subtasks that can be processed in parallel. And for example, a nice example would be analyzing different sections of a document or evaluating a product from different perspectives, or even a report from different perspectives. And the results are then aggregated with the aggregator into a comprehensive response and cater as an output. And the voting runs the same task multiple times, potentially with slight variations in prompting, in order to get diverse perspectives or to produce a higher vote of confidence for the final output. This is particularly valuable for tasks when there's no single right answer, and or the redundancy improves the reliability of the result. The key advantage of parallelization is improved performance, both in terms of latency and of quality. The trade-off, again, unfortunately, is extreme computational cost, because we are basically, I'm going to go with spamming. We basically spam and use multiple LLM calls a lot of times at each run. And in the code here, we have the parallel function. I'm using the thread pool executor from the Python standard library, and the two lines under, the futures and the return, are basically list comprehensions. By the way, do not use that code for production. It's not it doesn't follow the system of Python. It's not explicit, and it won't help for the poor soul that will have to review it. So in any case, here I basically use a thread pool executor to manage parallel execution via Python, and each input, as you can see at the future statement, is formatted with a prompt and submitted to an LLM call. And finally, I return the results. Now, we've talked about some simple patterns, and I want to talk about two distinct advanced patterns. You might be wondering, yeah, okay, what's the difference here? Advanced patterns basically build upon the things that we have already explored on similar workflows, on routing, parallelization, and prompt chaining. And what really makes them advanced is their ability to handle more sophisticated tasks through dynamic, adaptive processes. You will see what I mean in a minute when we go over the code. These patterns, so where do these patterns sit? If you remember the complexity spectrum from a few slides ago, these patterns sit between the simple workflows and the full agent architecture. So in essence, when our simple patterns don't cut it, they are not sufficient for our needs, and we don't want to go ahead with a full agentic architecture that introduces a whole other deal of complexity, and basically it will be overkill. Then we can go with advanced workflows, which basically represent our middle ground. Let's go with the first one, the orchestrator workers pattern. Here we have a pattern which is quite flexible. I know this is not represented on the diagram, but it is quite flexible. It offers us nice ways of handling complex tasks that benefit from decomposition. Tada, what did I just say? Unlike simple parallelization that we talked 3 slides ago, here the number of tasks are not predetermined. We don't have to break into 4, 5, 15 tasks. We don't know how many tasks will be produced. So this pattern uses a central LLM to dynamically analyze the results, analyze the inputs, and break down those tasks and coordinate with specialized workers on how to handle them. So you can visualize it basically as a manager. The orchestrator acts as a manager, determining what work needs to be done and how I can distribute it. And afterwards, the orchestrator maintains a high-level understanding of the overall tasks. It keeps the big picture, and it delegates the specific aspects and the execution to the specialized workers. And after the workers complete their tasks, the output of those workers is synthesized with the help of the synthesizer, and it's put into one cohesive final result. And the pattern, if you have used Cursor, the AI editor, You're probably already familiar with this pattern. This pattern excels in scenarios like complex coding tasks where multiple files need to be modified, or content creation that requires different specialist perspective. Imagine an even bigger marketing campaign that has that requires the feedback from other departments apart from marketing. So with this pattern, we can allow our workers to focus on the execution, on what matters the most, and then they do the best, and the orchestrator basically maintains the whole process as is. I decided to go first with a code here before the trade-offs. As you'll notice, the code here starts becoming a bit more complex, even if we take away the comments that I've added. We basically have a single task, a string, that returns a dictionary of results. And as already described, the orchestrator asks the LLM to break the tasks into subtasks. It's the for loop. And at the end, all worker results are collected in a list and returned in a dictionary. The trade-offs here, they are quite considerable. We have higher latency due to multiple sequential LLM calls. That means we have far more costs than we imagine, especially the costs are greatly increased. And because we perform a lot of model invocations, as you can see from the code, the complexity is greater as well. That being said, the quality of the results is unquestionable and greatly justifies the added complexity and the costs and the latencies. And the last pattern of the 5 is the evaluator optimizer. Again, I think you are already familiar with that one from the various AI applications that are out there. This pattern basically implements a feedback loop, a smart feedback loop for iterative improvement. It separates content generation from quality evaluation, allowing each to be optimized independently. We don't have to care how much work we throw to the LLM call generator because we're working with the LLM call evaluator. Again, remember, separation of concerns. So how does that work in practice? A generator LLM creates initial content, and then the evaluator has to assess this content with specific criteria and provide structured feedback. This feedback is then incorporated into the next generation attempt, and the process continues and so on and so forth until the output meets the defined quality criteria. This pattern is particularly effective when we have clear evaluation criteria. We know what we want to evaluate or measure, and iterative refinement provides measurable value, meaning that we know that the first solution is not optimal. It more or less mirrors the human creative process. When we start to create something, we write down, we review it, we even critique it, and iteratively we improve it until we arrive at something that we're satisfied with. And this pattern, especially this pattern, shines in scenarios, again, like content creation, but also about code generation and generally complex solving scenarios like research. Unless, of course, your code runs on the first try, so you probably don't need any LLM-assisted tools. The trade-offs here are similar to the ones we had with the orchestrator workers pattern, but there's a catch. Because after a few iterations, let's say 4 or 5, we might hit a point of diminishing returns where it doesn't make any sense to continue with the feedback loop. Again, the code here, far more complex than the orchestrator workers one. And we can notice the evaluator and where that takes place. It's inside the for loop, and you can see that we can check if a solution meets the requirement with the if pass statements. And what I want you to focus on is on the first line, on the function definition, where I define the max iterations, and there are 3. It's the threshold that I told you on how many times we want to run the feedback loop. this this slide is basically for me, so I can catch my breath and take a break. And in order to have at one place everything we've talked about, the 5 different patterns, and what I want you to keep in mind is that we can always add complexity. And yeah, when we have to scale AI applications, it's inevitable. And most of those times, we need to combine strategically the patterns that have already been mentioned, based on our use case, of course. Now, say it's Friday, right? And you might be working on Monday, and an AI project arrives as an email, and you want to have a roadmap, a compass on how to tackle it and approach it. And that's why I try to summarize everything I've talked in this presentation with this roadmap for implementing in our own projects, on work or on personal stuff. So, as you want to see first, on the top, we build minimum viable solutions. We basically go the same way as I opened in the presentation. We go with the simplest approach first. Usually that means a well-crafted prompt, and we might even add some basic context retrieval, but not something fancy. And in practice, this usually solves most of our problems, or use cases in this regard. Really, it's surprising. The goal here, in any case, the goal here isn't to attain perfection from the first try. It's to establish a working foundation quickly, which leads us to how we measure our baseline performance. Before making any changes afterwards, we need to establish clear metrics that matter for a specific application. That means costs, latency, cost per query, and above all, user satisfaction, always taking into account the user feedback. Because without this baseline, you won't know if your improvements are actually improving anything. And moving on, afterwards, we need to be in a position to identify specific limitations with our application. We must look for concrete pain points. For instance, do the responses make sense? Do they keep the consistency or not? Is our system struggling with complex queries? These are things that should be documented because they can guide our next steps. At number 4, there is the decision framework on how we add our complexities. Hopefully, by now, this is where the patterns that I've just described to you will come useful. And based on what you are seeing, you will tackle the problems accordingly. For instance, say you are seeing inconsistent quality between your prompts, right? So you may have to incorporate an evaluator optimizer pattern, or the tasks need breaking down because they are well defined and you know their evaluation criteria. Then maybe an orchestrator worker is appropriate in this case, or the case might be even simpler, and you can go with a prompt chaining approach. And after measuring the improvements and the target complexities and all of that stuff, we must be at a position to quantify the results of what code we are writing. In this case, what I mean by that in practice is basically things you've heard all over. Run some tests, A/B tests, automate your evaluations, collect user feedback. That improvement should be substantial and quantifiable, because that must be clearly tied to our business objective of the application. We don't write code in vacuum. And based on that, and this is something that I want to emphasize here, we must be ruthless with the results. We must keep complexity that only delivers measurable value, and any improvement or any new pattern or feature that we add should vastly outperform the increased complexity. I know the percentages might sound weird, but you don't want to debug AI applications. Code is ephemeral. The code we're writing is ephemeral. So don't be afraid to revert to simpler approaches if the benefits just don't materialize. You'll just write more code. And with that, we're coming to the end. I hope you'll find these patterns and principles useful while checking how you will integrate your LLMs. And the key takeaway that I want you to remember is that effective integrations with LLMs basically means finding a delicate balance, that sweet spot between simplicity and capability. Thank you.